So today we will discuss three groups. Let GI be any non-empty collection of groups. Now define capital G to be the collection of maps from J to union GI such that so this is basically what? This is basically a Cartesian product. You can see Cartesian product of GIs. This is how you define Cartesian product. Now we will define a group structure on G. So for any G prime in capital G, we define G prime from J to union of GIs J by equal to G right, for every I belonging to G. Right. So GI and G prime I, they are both they are in capital GI. Right. So this is G prime is well defined. You can see because this GI and this G prime I both are in capital GI. From here you see. With respect to this binary operation capital G is a group. You can see that if capital GI, this is collection of abelian groups, right? Then capital G becomes abelian. You can see very clearly. Note that if is collection of abelian groups, then capital G is abelian. A group G defined in this way, right? That is by taking a Cartesian product. This way is called direct product of the collection this direct product, it is denoted by this. So direct product of a collection of groups GI is denoted by this symbol. We have another definition. Let GI is that IJ be a non-empty collection of groups. We define B product of this collection of groups GI as a subgroup H of the direct product this, such that G belongs to H implies that GI in capital GI is identity. This is identity for all I in J except finite many. my okay. uh, we denote the big product by this symbol also. Sometimes big product is called as direct sum also, right? Sum. Sometimes big product is called direct sum, called as direct sum, right? So notation for that is something like this. So let me just explain a little bit more. So when you have direct product, right? So here elements are what? Tuples, you can say, right? So you can, though it is this capital J may be countable, may be finite, it may be countable, it may be uncountable. We don't know. So it is not means uh, 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 proper to write it in this way, but means if suppose J is countable, so then we can always write something like this. So x1, x2, x3, and so on, xn, right? So this infinite tuple, right? So elements of Gi, this uh, direct product Gi, will look like this, right? So this will correspond to what? This will correspond to that G in this, such that Gi equal to Xi, right? Okay. So this is how the elements of this direct product will look like. Now, what will happen when you consider a big product, right? So its elements will look like this, right? So you will have at means all the places you will have identity, right? And then you have x1, then x3, x2, something like this, x3. So at all the places identity will be there except at finitely many places. Okay. So you can see that elements of this are also elements of this. Only difference is that all the elements of this are of this kind, right? So at all the places, you have identity except at finitely many places, right? So it says that Gi equal to identity for every I belonging to J except for finitely many I's. Okay. Next, so just a minute. So if J is finite, if J is finite, then direct product and weak product or direct sum, they coincide, right? They will be same. If J is finite, then this I J. This is same as this. right? Direct product and direct sum will be same. Uh, next, we have following definition for free product of group. Free product. Groups. Let I, J, we are using this notation for some. Let G alpha such that alpha belongs to G. The subscript we are using differently. Let this be any non-empty collection of groups. Define the star alpha, this to be collection of elements G1, G2, Gm such that Gi belongs to capital G alpha I is not an identity element. For every I equal to 1, 2 and so on, and alpha I is not equal to alpha I plus 1. So star alpha G alpha is collection of those, you can say that these are words, right? So this is just, what is this? You can ask what does this mean, right? You can ask that what is there some product? What is it, right? You can always ask, right? So I would say that it is just, so you write some words, right? So when you write some words, you write, suppose you write 2, right? So these letters you just write side by side in some order, okay? Then you get some word, right? So this is collection of words, just collection of words, right? So in a word, you will have finitely many letters, okay? So if this is a collection of words where letters come from these G alphas, okay? Here, of course, these GIs, these letters are not identity elements of these G alphas, right? So we avoid taking G alphas, GIs to be identity. So we don't take GIs to be identity. Also, these consecutive letters we don't take from same G alpha I, right? So consecutive letters we don't take from same G alpha, right? Suppose if G1 and G2 are from same G alpha, then we will consider G1, there is some operation in G alpha. So we can multiply G1 and G2 and we will get a single element of G alpha, and we can put that here. So to make the definition of this star alpha G alpha precise, uh, we will clarify a few things. Just first, so this star G alpha we have defined like this. Now we will define a binary operation, and then give some clarifications. Define a binary operation, right? In order to make this group, we will define a binary operation in star alpha G alpha by. So elements of this will be of this form: G1 to and so on Gm, right? And another element we can take H1, S2, and so on H. There is no comma, right? So there is no comma. So H1, S2, and so on Hn. So how we consider, how we define this binary operation? We will just make another word Gm just by putting this word, right? H1, S2, and so on Hn, right? So it is something like if you take two words like this, 2 and then 3, okay, then how will you multiply these two according to this rule? You will just put 2 and then 3. Okay, so this is the multiplication of this and this. Now we will so in order to precisely uh, define this binary operation, we will give some clarifications. So if Gm and H1 belong to the same G alpha, then they should be combined to get a single letter GMH1, right? So we had this G1 to Gm, then H1 is to Hn, right? So if Gm and H1, right, they belong to same G alpha, right? They belong to same G alpha. Then because G alpha is a group, so Gm H1 will be a single element of G alpha. So we can combine to get a single element and then we. So that because in the definition of this star G alpha alpha, we have considered that the consecutive letters don't belong to same G alpha, right? We had the condition alpha not equal to alpha plus 1, alpha I not equal to alpha I plus 1. Okay. So this if Gm and H1 are in same alpha, then that condition will be violated. So we will consider the product of this Gm and H1 in G alpha, and you write to replace it by that. So suppose this is suppose it is U, so we will replace it by U. This according to to the multiplication in GL. And if this new letter GM H1 happens to be identity of G alpha, it should be cancelled or removed. Cancelled or removed from the product. If GMH1 happens to be identity of G alpha, then we will just remove it and we will write what? We will just write G1, G2, Gm minus 1, and then GMH1 we will remove, and then next we will write H2, right? So we will write this one, H2, H3, and so on, Hn. Now this allows Gm minus 1 and H2 to be combined if they are from same G alpha, right? So this may allow Gm minus 1 and S2 to be combined. And possibly cancelled too, right? If they are if their product is identity, and possibly cancelled. Now what will be the identity in this, so it will be the empty word, right? A word containing no uh, letters, right? So we allow empty word to belong to star alpha G, right? Next, this with respect to with respect to above binary operation, this star alpha G alpha is a group. So identity means this empty word, right? So if we have a word, if we combine it with empty word which has no letters, then we'll get same word, right? So this you are supposed to accept this, uh, right? Uh, Logically, there should not be any problem. Uh, so this alpha G alpha is called is called free product. It is called free product of the collection of groups of groups. We have a definition. So we have defined free product of a collection of groups. Next, let S be a non-empty set, a define G alpha equal to alpha m such that m belongs to Z for every let me write this way, alpha to the power m, but yeah, so yeah, we'll write this. So what is this alpha to the power m? This is just a notation, right? This is just a notation, right? Uh, And this for every alpha belonging to S. Note that G alpha is a group with respect to the binary operation alpha m alpha n equal to alpha m plus n, right? Also, G alpha is isomorphic to Z for every alpha in S, right? Now a free product, sorry, a free group on S is the free product star alpha in S, G alpha of the collection G alpha. This we have just defined what is G alpha here, is the free product this of the collection these groups. Here S is called basis of this alpha. Yes, this and cardinality of S is called rank of the free group. So we stop here today. We will discuss